The Set Theory Guide for Artists podcast.
The lies that we tell ourselves in order to survive. The whirlpool turns of our lives. The delusions that hold on for long enough for us to step upon the stone to the next moment. What's that now? What's this? Ah, yes, this is the Set Theory Guide for Artists. Excuse me, I got carried away. I thought I was getting ready for my open mic poetry night. Ah, well, we all get a little carried away sometimes, don't we? But anyway, I hope you enjoy this podcast. The whole world.
We are waiting in an elevator. Not waiting really because we are never without, but we sense that it would be more fun if the artist were here. There's only one button in the elevator, and it is an arrow pointing up. The doors open and close, but there is no one there. We think about our own existence and wonder if there is someone watching us like we watch the artist. We are glad not to have a body because we might need to sit down. Is the elevator safe and sound? The doors open and it is the artist. She walks in, turns around, and pushes the button. The door opens again and we follow the artist out of the elevator. The artist looks down and sees the whole world. She sees the man and his paths as he travels the world. She wants to be like him. She even feels a little envious. He is a famous artist in some circles. And she feels like she is behind or will never be able to get what she wants. Learning about Ehrenstein trees and Hausdorff gaps on her own made her feel confident, like she could do anything. She thought that the mathematician might be wrong about how many colors there were on the spectrum, and she decided it could be more than the cardinality of the continuum. When she worked as a waitress, there was a regular that would talk about his near-death experience and said there is a blue in heaven unlike any blue here on earth. Suddenly everything was swirling and she felt ungrounded. In the past week, she hadn't done anything but read about set theory and was feeling the need to live life. She signed up for a glass blowing class. Well, she also applied for a graphic design job in a place that might offer her more freedom and opportunities. She liked this new plan, and okay, it would put her a little closer to the man. She wanted him, and she wanted to be like him. We observe the artist talking to herself, gesturing. We zoom out and see that she is on a catwalk of a theater, looking down at a set with a map of the world. I remember writing this and I just wanted something like, you have no idea, like we have no idea what's going on, where she is, something magical is happening, and like she's like observing the set. And it's also the setup for the play to come later in the next chapter. Oh, and is the elevator safe and sound? I know that there's a song that I really liked that I was thinking of there. Capital City or something? So this is nice. I kind of sometimes forget what I wrote, so that's nice. She's still wondering what's she gonna do. Yeah, I think she should get a microphone, get set up. Sounds like she wants some theater in her life.
Chapter 1, Part 3. It will get weird. It's not weird already, though. It hasn't been weird yet, though. It will get weird, though. It will get weird.
Part 3. It will get weird. The sculpture is the Endless Column by Brancusi, 1918, assembled by this engineer, Stefan. To end chapter 1, we get an idea of what is to come in the universes of set theory. We deconstruct our mathematical world in order to understand our foundations and stretch the limits of infinity. In this section, we will introduce a discussion of languages, models, elementary submodels, Skolem functions, and the Lowenheim-Skolem downward theorem to get a hint of the strangeness of set theory. A language is a collection of symbols with some meaning. In logic, a language is also a collection of symbols. It is the function, relation, and constant symbols. In addition to the symbols of the language are the logical symbols, including variables and punctuation. Equals, parentheses, x, y, z, negation, union, or, and, there exists, for all, x, y, z, which combine with the function, relation, and constant symbols to form the terms and formulas of the language. The language of set theory consists of just membership relation. In the next chapter, we will see how to convert a statement in words into a statement in the language of set theory. A model A for language L includes a universe of numbers A and an interpretation of the symbols of the language in the universe of numbers. For example, the language may have a plus function symbol. The interpretation of the symbol plus to the A in a model of arithmetic is the real addition function that means what we mean by addition, and we will often conflate the two. The natural numbers are a universe for a model of arithmetic. But what is our universe of numbers in set theory? It should include the natural numbers, omega plus 1, the real numbers, and many more. What counts as a universe of set theory is central to set theory, and we will discuss more in Chapter 3 on set formation and Chapter 2 on the axioms. The language of set theory consists of just one binary relation, the membership relation, epsilon. In order to interpret the membership relation, what the membership relation means, we have to know what counts as a set. For example, is the union of sets a set? Is the image of a set under a function necessarily a set? Having a model of set theory implies that we know what a set is, and the axioms in the next chapter describe the various collections that count as sets, starting with the empty set. Let us think about the formulas of a language. For example, phi of xy is defined as, phi of xy is defined as x plus y equals 2. Is a formula in arithmetic, and we can find different values of x and y such that the equation holds, such as 1, 1. We can write this as phi of 1, 1 is 1 plus 1 equals 2. Let M be a model of arithmetic. Then the way to write that this statement is true in M is to use the satisfaction symbol, which is a meta symbol just for us so that we can talk about models and what they think. M models phi of 1, 1. We say M models phi, or M thinks phi, or M satisfies phi, or phi is true in M. A model is like a production of a play or movie, where the language and the logical symbols are the script. The intended props, the language are the logical, and the logical symbols are the script, the intended props, and the set design. The universe of numbers is the cast, and the director and producers interpret the language to create the production. The satisfaction relation is like saying that something happened in the play. The Scullin functions, which we will see next, play the very important role of casting directors. We will talk about formulas and terms a little bit here, and in the next chapter we will dig into more details. Examples of terms are 2x, x plus y, x plus 2. The terms include and are built up from the constants, variables, and function symbols. Examples of atomic formulas are x plus 2 equals z, x plus 2 less than x plus 3, x equals 2. The atomic formulas are terms with relation symbols or the equality symbol between them. And then more formulas can be built up from atomic formulas. A term is a part of a formula, and a formula is saying something about its terms. A function symbol on its own with variables and constants is not an atomic formula because it is not saying anything until we add an equality symbol or relation symbol or another term. A relation symbol and another term. A term is like a set with two chairs and a table with an apple on the table between the two characters. While an atomic formula is one character picking up the apple and attempting to take a bite. Then this can be built up into a bigger formula where the other character is trying to stop them, and these build up to create a scene. Consider the formula x equals 2. In this formula, x is a free variable because we could let x be 2 and get 2 equals 2, which is true in a model of arithmetic. And if we let x be 3, then the formula is 3 equals 2, which is not true in a model of arithmetic. M equals n plus times 0, 1 less than. That's the model of arithmetic. If phi of x is x equals 2, we can write the above observation with the satisfaction relation as m models phi of 2. or M satisfies phi of 2, and M does not satisfy phi of 3. If we add quantifiers, the formula x equals 2 no longer has free variables. A formula with no free variables is a sentence. The sentence, there exists x, phi of x, means there is an x such that x equals 2, which is true in M. M models, there exists x, phi of x. The sentence, for all x, phi of x, means that for all x, we have x equals 2, which is not true in M. So M does not model for all x, phi of x. Let A be a model in a language with universe A. Consider a formula phi x a1, a2, up to an, where x is a variable and the ai's are constants in A. Suppose there is an A in A such that A models phi of a1 up to an. A Skolem function h from A to the n to A for phi assigns the sequence a1, a2, an to a solution of phi, aka A models phi of through h of a1 up to an, comma a1 to an. That is, if h is a Skolem function for phi, then there exists an x in A models phi of x a1 to an. Implies A models phi and h of a1 to an, a1 to an. A Skolem function is like a casting director for scene phi, where when all of the roles except for one have been filled. For this scene phi, the casting director H can find the right person to fill the role from a set of players A. If there is a role to fill for the scene, then given that all the other roles have been assigned, the casting director can assign the role and can do so for any combination of players filling the roles that have already been assigned. Let X be a subset of players in the universe A of all players that can possibly be assigned roles in the production. In each scene, phi assigns all but one role to players in the subset X of players, and in each scene phi assign all but one role to players in the subset X of players, and consult with the casting directors about casting the final role. And do this for every possible combination of players X in the scene. There may be a situation where there is a scene which needs a role to be assigned, and the only person in A that can fill the role is a player not in X, so they are avoided to join the cast. The final cast list is the Skolem whole of X. If our language is countable and X is countable, then the Skolem whole is also countable because for each of the countably many scenes, we only had to pull in a finite amount of additional players for an overall countable Skolem whole. A submodel, subproduction, B subset of alpha, is a subset, B subset of A, with relations, functions, and constants restricted to B, enclosed under functions with constants in B. A model B is an elementary submodel, elementary subproduction of A, written B, elementary submodel of A, if for every formula phi in any A1 to AN and B models phi of A1 to AN if and only if A models phi of A1 to AN. That is, for any scene that works with players from B in production B will also work for production A. Elementary submodels satisfy the same first-order sentences as the original model. That is, an elementary subproduction will have the same scenes as the original production. We can construct an elementary submodel B subset of A if we guarantee that there exists X in A models phi X A1 to AN, where A1 to AN are in B. Then there is an A in B. If we guarantee that if we have this, there exists an X in A models phi of with X A1 to AN, where A1 to AN are in B. Then there is an A in B such that A models phi of A1 to AN. That is, B is a subset of A, is an elementary subproduction if whenever there's a scene with all but one role assigned with players from B, then there is a player in B that can fill this role. This is the Tarski-Bott test for elementary submodels. If X subset of A is a subset of players, The skull and pole of X will form an elementary subproduction. Imagine not just a production of a play, but the entire production of set theory, including the production of all of mathematics. Call it D. One day there was a big storm, and the only way for the players to get to the theater was to take a bus which had only countably many seats. My vision, we might be okay. Looking at the cast list. Can the show go on? Can the casting directors find countably many players to pull off a show that includes, for example, the uncountability of the reels? Indeed, the show must go on. The show can go on by the Lowenheim-Skolem downward theorem. Every infinite model for a countable language has a countable elementary submodel. Ever feel like something is out of reach and then you go to it, but it is not totally satisfying and you want to reach for more? This is the nature of life, and this is the nature of mathematics. Mathematicians try to capture mathematics, but she will always elude them, and this is why they love her. We will see that Gödel showed that mathematics cannot prove its own consistency. There are also independent statements in mathematics. Cohen showed that CH is a statement which is true in some universes and false in other universes with forcing, which we will see in Chapter 6. The method of forcing that developed after Cohen's breakthrough has a lot of strange and interesting interactions with large cardinals. In Chapter 7, we will see how to use forcing to softly kill large cardinals and degrees of large cardinals, and thus witness a delicate battle between the great power of infinity and the great power of the changeability of mathematics. And then the guy at the end says, what is the deal with zeros and ones? So for the part 3 of each chapter, I wanted to always do something a little different, kind of give us a break. Also, maybe not so visual necessarily. I don't know if I'm going to hold to that, but kind of give our eyes a break, tell a story, something weird, something kind of interesting. And because the next part is going to be the painting, so kind of getting our eyes ready. So I did want to kind of like a cadence to the chapters where it's like sort of the height is the part 2. The part 2 should be the most proofs and the most images, and part 1's kind of a warm-up. Part 3 is kind of a let's take a break, let's read a story. Wait, I don't know how much that continues. I'm thinking right now about I'm on a part 3 right now in real life, and I'm thinking about how to write it. So, but that's the idea. I didn't really want each chapter to be so uniform and this is like a textbook and then we open up with a definition. I also noticed here that I do a lot and I should keep doing is before I introduce I don't just start with the definition. It's just oh, you just learned it. You just learned something. Oh, this is called, the thing you just learned was the Lowenheim-Skolem or the Tarski-Vaught test. I like that. Okay, and I think also writing this helped me kind of think about, it's kind of dramatic, last paragraph here, but I do think about my thesis and the power, the changeability of mathematics is forcing this power, but then there's also these large cardinals which is infinity, and so there's these two big parts of math, and I think that a lot of people don't know about the changeability of mathematics. But just on from the very zoomed out perspective, but and then so that I think that the whole area of research forcing in large cardinals sort of explores this battle.